Welcome everyone. In this video I will try to convince you about the fact that you cannot build a reasonable AC by using Peltier devices, and I will go through the datasheet of a certain Peltier device, a thermoelectric cooler, and then we will do some very easy math just to prove you, just based on the math and simple common sense, that you cannot really build a reasonable air conditioner. So a lot of people tries to do that, and a lot of people are uploading videos about some structures or some kind of things that they call AC, but I'm pretty sure that they don't work as air conditioner. So first of all, let's learn how to read these performance curves. So these performance curves will basically tell you that at a certain temperature gradient, so temperature difference between the hot side and the cold side, how much power you can basically pump with these devices. So if you take a look at this curve is defined for 50 degrees Celsius hot side, and this is like optimistic estimation, because usually you have it around 40-50 degrees if you have, let's say, this 15 ampere TEC 12715 unit running on its maximum load or maximum performance, which I mean that 15 ampere is running through the device. So if you haven't checked my previous videos, I strongly suggest you to do that, because I explain a lot of things about the cooling capabilities of these devices. And I also talk about some different measurement methods. But here it's more about the theory behind it, or more like the investigation of the different technical stuff. So what you can read from this chart is that you see the dt here on the x-axis. So that is basically the temperature compared to the hot side temperature. So what this means is that if you have, now just let's write down the variables. So we have the hot side and then we also have the delta T. And how we get the cold side temperature is basically we just combine these two. So that means that we just take the hot side temperature and we subtract the delta T from that, and that will give us the cold side temperature in Celsius, of course, here. So I just write down the numbers. So here, which is at 0 degrees difference, so the hot side and the cold side are at the same temperature. This means that the TC is also at 50 degrees. Here we are at 40 degrees, and 30, 20, 10, and then 0. So now we are reaching some lower values, and minus 10 degrees, minus 20 degrees, and minus 30. So I think this is like quite understandable. And then you see on the y-axis that the cooling power is defined in watts. That is not the same power as the device is using when you connect it to the power supply. This is the cooling performance that it can provide you. So let's see what happens on this curve. First of all, let's check this. Usually most of the videos, and I also have some of those videos, they say and they show that they can reach minus 40, minus 50 degrees with single or stacked Peltier units, and they are very happy about it. And I was also happy. This is a nice thing. But then you have to consider that if you are somewhere here in this curve, let's say you are in this corner here. If you go and draw a line, then you are basically at, like, I don't even know, 10 or even less watts of cooling power. So of course you can reach very low temperatures, so you can have very high dt or delta T values, but then you will not be able to cool anything. And that's just what happens. So basically, when you run your empty Peltier device and you are able to cool the hot side enough that your hot side temperature instead of this is, let's say, 20 degrees, then if you take these delta T's, let's say the delta T equals 80, just to, let's say, overestimate everything, then you should be able to go down to minus 60. But then you have different effects, and you have the heat loss through the environment, basically, and so on. So you end up somewhere around minus 40, let's say. But then you are not able to transfer heat at all. So that's what you have it in this corner. And this you really have to process this or digest this. If you can reach very cold temperatures on the cold side of the Peltier unit, that does not mean that you can cool down anything to that temperature, or that you can cool down anything to any temperature at all. Because basically, if you can have this very, very low temperature, that means that your QC is very low. So you are basically just balancing out the heat, which is like escaping to your cold side from the environment, because you haven't surrounded your Peltier cooler with proper insulation, and so on and so on. So this is not the case. If we want to do something more, which makes a bit more sense, then we can do the following. So how you read this chart is, let's say we want to produce 30 degrees delta T. So that's nice and cold delta T equals 30, degrees Celsius. So that means in our case that the TC should be, of course, 50 degrees Celsius minus 30 degrees Celsius, so that's 20 degrees Celsius. So this means that your cold side will be 20 degrees, but let's check what happens. So here you draw a vertical line, and then you see that these curves intersect these other curves, which are defined for different currents. So you do another now horizontal line, so you basically go and cut the y-axis. And now let me write down just these numbers for the currents. So we have 3 amperes, we have 6, and of course 9, 12 amperes, and 15 amperes. So the way you read this curve is the following. You pick a delta T based on your requirements of the cold side temperature. In my case, I want 20 degrees. And that means that the delta T is 30 degrees if my hot side is assumed to be 50 degrees Celsius. So you draw this vertical line along the line of the 30 degrees, and then you draw the horizontal lines where the vertical line crosses these different curves for the different currents. And then you read where the horizontal line meets the y-axis, which is the QC. So the first, let's say that's around, so this will be the current, and this will be the QC. So I just try to draw columns, and like this. So this is, let's say, 6 watts. So then this is nothing. So we can see that even though we don't have that high delta T, then at 3 amperes, which is of course just 20% of the performance of this device, it cannot really do anything. So that's 6 watts. That's not even enough to cool down a large bottle of water. Then we move up to 6 amperes, so we double the amperes, and then now we have something more reasonable. Let's say this is 45 watts, and then we go up again by 50%. So these are basically from here to here, it's 50% step, so 150. Then at 9 amperes we have now 70 watts. So this is like a strong light bulb. Nowadays I don't know if you can buy these because everyone is buying LED, but in the old times it was possible. 12 amperes, so we are, let's say, 85 or 85-ish. It's a bit lower maybe, or higher. And then let's round it up to 100. So let me highlight this. So if you run the maximum current through this device and you are able to keep the hot side temperature at 50 degrees and your desired cold side temperature is 20 degrees Celsius, therefore your delta T is 30, then you are able to pump 100 watts of power with your Peltier device. But now comes the fun fact. This is just the heat that you can pump out, and what you have to consider that you have your Peltier device. Let's say this is the hot side. Then your device looks something like this. So in between the hot and the cold side, of course, you have the basically the semiconductors. So let me write it down. Semiconductors. So what happens here is if I magnify this and a bit simplify, so you have this let's say heat reservoir, which is the cold, and then you have a pump, which is basically the set of semiconductors, and then you have the hot side. So what happens here is that you pump the heat from the cold side to the hot side by running a large amount of power through your semiconductors. So here the QC is in the way, but here you also put in work. So basically what happens here is that you have to consider that you run this device at 15 amperes, and that happens roughly at 15 volts or maybe 16, but so we now know that P equals I times U, so this is 225. So you basically generate 225 watts of power, which appears on your hot side, and this is just one unit, which appears on your hot side, and you have to get rid of this. So just think about the traditional AC systems. So you have these huge external units where they basically base the condenser, and it's a very loud, huge box, and that's where you get rid of the huge heat which was like carried out from your room. So now you have 225 watts for one unit, and for that you can only pump out 100 watts. So let's I just did some Google search, and one thing which immediately came up, an AC unit which can cool a room with 28 square meters of floor area, and the cooling power of this, not the power that it takes from the outlet, but the cooling power was 2000 watts. And then this unit has 100 watts. So we need, let's write a shopping list. So one device is 100 watts, and we need 2000 watts. That means that we need 20 devices, right? What does that mean is each device, roughly, if you buy it from China, $5 US. So 5 times 20, $100. Okay, this starts to get expensive, but that's not the expensive part. See this number and this number? Each device you have to add 225 watts. So I just checked these independent units, which you can buy for example, LED strips. So I checked 24 watt power supply, 24 volt and 20 ampere power supply, and this is roughly $30 per each unit. And I say that, okay, we might say that we sacrifice a little bit of power, but we don't consider the different numbers. We still say that, okay, 100 watts, but instead of buying 20 of this to provide more power to this than we should, we just buy 10 units. So each of these power supply will provide power for 2 units. So we don't waste that much money. But then this is already $300. So now we have our Peltier coolers and we have our power supply for it, or power supplies, and we are already at $400. And let's come back to this part here. We have 20 units, right? So 20 units, and each unit, if you check the surface area of it, is 40 by 40 millimeters. So you can make a grid of this. Let's say you can place them nicely close together, but you cannot because of the cables. So you can place them more like a rectangle, and rather a rectangle than a square, because these devices are something like this. So you cannot put more than 2 next to each other nicely. So you cannot have, let's say, a 4x4 row of them, because the middle units will have problems with the cable. Or you can drill through the heatsink, but that's too bad. But let's say now we don't care about the cables because we are just curious about the surface area. But this basically creates, let's say, a 4 by 5 unit. So that means that in one direction you put down 4 units and the other direction you put 5. And then that's how you make up the 20 units. So I just try to draw nicely. 1, 2, 3, 4, 5, and then 1, 2, 3, 4. So something like this. And this is your 20 device. And then the shorter side will be 16 centimeter, and then the longer side will be 20 centimeters. So that's a quite big area. And then you have to remove the heat from the hot side, from this big area, and you will probably need either water cooling or something. And you have to remember that you have to remove the heat out from your room, because if you keep the cooling at the same room, then you warm it up, but you don't cool it. So then most probably you will end up with water cooling. So the water cooling is quite expensive. You can maybe use some cars water cooling, but that doesn't make sense too much. And maybe you will need to build a customized heat exchange plate where you can fix these. And then you have the other side of the Peltier cooler. So this is, let's say, this is now the cold side, and that has to be in connection with your room somehow. And of course you need some, let's say, heatsink, and then you always need some fans to move the air, because otherwise, if you cannot move the air through the through the heatsink, sorry, then of course you are not able to cool down the air in your room. So I would say that roughly $600 or maybe more, you will end up with that to build a Peltier-based device which can work somewhat as an air conditioner and can provide some cool air. But I'm pretty sure that the outlet temperature of the ACs, the proper ACs, are much lower, or at least significantly lower than 20 degrees. So then we might need, let's say, 40 degrees difference of temperature. So if you just quickly look at this curve, then you see that then you cannot even run your device at 3 amperes, and then this becomes something like I don't know, 28, and then this becomes something like let's say 50, 52, and this becomes, so you go from 9 to 12 amperes and you stuck at 70 watts, and then you go to 15 and you are somewhere around not even 80 maybe watts. So you lost a lot of cooling power. So if you really want to cool, and what I mean is you are really able to remove heat, because cooling is not maybe it's a wrong phrasing, but cooling is not about decreasing the temperature in a sense that you just get a smaller number, but you have to remove the heat from a system. So and that's a lot of work. So of course, if you remove the heat, you decrease the temperature of the unit. Let's say you don't have phase transformation, like you freeze the water, because then that's a different story. But if you think about the air and you just want to cool down the several cubic meters of air in your room, that's purely just pumping out the heat. And as you pump out the heat, you will be able to decrease the average kinetic energy of the air molecules, and that's basically their temperature. So then they will cool down and you will feel that the air is cold. But you can see that this is not as simple as you would think. So don't be too confident by being able to reach, let's say, minus 20 degrees on the surface of your unloaded Peltier cooler, because you will not be able to make it into a proper AC device. And you can see that one device, which is 100 watts, is just perfectly not enough to provide cooling for your room. And just imagine that you have tremendous losses through the wall by opening your window, and you are also, as a human, heat source. So, and also you have your devices inside your room. Maybe you can cook in the room where you want to have the AC, and so on and so on. So that this will not really work. So let's check the price of an AC unit which is capable of doing this 2000 watts. So this unit which I checked, this 28 square meter, it's a portable unit, but of course it has its exhaust to both sides, so you can push the cold air into your room, and then you have to get rid of your let's say created heat somewhere. So this device, which is for 28 square meters and again 2000 watts of cooling power, costs around $300. And then $300 can buy you a device that you just plug in into your outlet, let it run, and it does everything for you. Probably it takes up much less space and probably creates less headache than building this device. I'm pretty sure that maybe you can short some circuits or do some chipping of these very delicate Peltier units. You can easily break off the ceramic plates, especially their corners. So this will not work. So please believe me that based on these numbers, and this is really just a hand-waving calculation, but it is basically this what you need to calculate. You cannot do this way. So you cannot build AC cooler. So all those videos you see, ask them please to show you the numbers. Show you, let them show you how long did it take to cool down their room, what was the temperature of the room, where did they put the heat, how much it cost regarding the electricity bill, and so on and so on. And at the end of the day, you will see that when you do the math and you do the calculations, and you see these are very, very simple calculations, and you can do it very easily, just multiplication, and basically that's all, and some common sense, that you really cannot do this. So just don't try it, because you can buy a brand new, nice, safe device which can do the job for you for a fraction of the price. So yeah, I hope that this did not sound as some sort of raging or something, but I just really want to show and tell the people that just don't try, because yes, it's a very nice experiment, but you will waste your resources and time on something that you might not be able to use. So if you just want to make some experimental stuff, I don't know, cooling down a cup of water or doing something like that, or building a miniature fridge. That can work. That can nicely work. You can see some products which are based on Peltier devices, and these are, let's say, miniature fridges or something which should keep the temperatures at very not very, but it's like a cool temperatures, so not even cold, but it's like let's say 14 degrees Celsius or something. That can work, but still it would require a lot of work to remove the heat from the hot side and keep everything tightly sealed and so on and so on. So regardless of these informations that might disappoint you if you wanted to build AC cooler based on a Peltier device, I hope that this video was useful and it was somewhat informative. And now I hope that you can learn how to read these performance curves or performance charts for the Peltier coolers, and you can look up these data sheets from Google easily. So I hope that this was useful for you, and see you in the next video.